This podcast is sponsored by QCon AI, the Applied AI conference for software developers. Focusing on the practices of artificial intelligence and machine learning, QCon AI takes a different tack than most other major software conferences in the AI ML space today. Rather than focusing on data scientists, QCon AI targets how full stack software engineers can apply machine learning and AI techniques in their day-to-day roles. QCon AI takes place in San Francisco, April 9th through 11th, 2018. You can find out more about the conference online at qcon.ai.
Welcome to the InfoQ podcast, a software engineering podcast from the people behind InfoQ.com. I'm Werner Schuster. Wes Rice, who normally hosts the show, is busy with QCon San Francisco this week, so I'm standing in. In this podcast, which was actually recorded at QCon San Francisco, I talked to Changhoon Kim, who is a director of system architecture at Barefoot Networks and is also working actively for the P4 language consortium. We talk about the new protocol-independent switch architecture, ASICs that promise multi-terabits per second of packet processing, and P4, a domain-specific high-level language designed for networking. It's a fun chat. Changhoon, welcome to the InfoQ podcast.
So you gave an excellent talk on making network switches programmable. I mean, why do switches have to be programmable? I mean, won't programmers just write bugs for them?
Well, I mean, programs help anything, right? You can introduce your own new cool ideas and then you can own it. Or if you have some unnecessary features built in fixed function form factor, you can get rid of them. I mean, to InfoQ crowd, programmability is just a natural blessing, isn't it?
Mm. Why haven't switches always been programmable?
So that's a great question. Up until recently, there was some non-trivial amount of penalty associated with programmability, especially for high-speed networking ASICs, because when you switch packets at billions of packets per second rate, or if you have to guarantee very low latency, say sub-microsecond in to out switching latency, programmability means additional logic, and hence your performance will be lower. You would have been lower in terms of PPS, and the power consumption could have been higher, and also the cost of building a chip could have been higher. So that has been there. Now we're in the silicon and networking industry. We're at an inflection point where such penalties are going away. And so people have realized that, programmability in the data plane is now doable, and we're actually observing a few commercial solutions that realize these visions.
You mentioned the word data plane.
Yeah.
I'm not a networking person.
Yeah.
Could you explain, I think, control plane and data plane to a novice like me?
Sure. So networking system or a switch or router always is comprised of data plane and control plane. And control plane is nothing but just a regular server kind of infrastructure. You have general purpose CPU like Intel, AMD, or PowerPC, and so on. You run a variant of Linux, and then you run a lot of networking specific applications such as routing protocol daemons and so on. But the interesting about networking system is that this control plane always needs what is called a data plane, and then it's essentially a high performance networking chip or ASIC that is connected to the control plane CPU through PCIe. So all the packets that this switch handles always arrive at the data plane, and then it goes through multiple stages and table match actions and then go out from the data plane directly to the wire. So packets do not come up to the control plane. What the control plane does instead is that this data plane has lots of tables, like IP routing tables. The contents of these tables are actually generated by the control plane and then lowered and then plumbed down to the data plane. So that's the division of labor between the two planes in every switch or router.
So let's get straight into the topic you talked about. You talked about two technologies called P4 and PISA.
Yeah.
So what are they?
As I said, networking system has two planes, control plane, data plane. Control plane is just a variant of Linux running a lot of networking specific applications. So it's software. So, developers like us can just easily, look at the code and then change it. And essentially, white box switches actually come with just vanilla Linux And you can download some open source networking apps like Quagga or Zebra, which essentially realize some routing protocol daemons. Then you build your own control plane. Nothing special about that. It's just another Linux server. But the data plane has always been built with fixed function chips, realizing some specific set of networking protocols in hardware, in hardware programming language such as Verilog, VHDL. This is, as I said, changing quickly. So the data plane chip can be also programmable, made programmable. And this kind of new data plane chip offering this flexibility is what we call PISA, Protocol Independent Switch Architecture. So we're actually observing a few incarnations of PISA architecture, which arrived at the market last year, and some of them are arriving in this year. A lot of networking industry companies are announcing that they will also join this trend, and then they will produce programmable data plane ASICs soon and so on. So that's PISA. Now, when you have this programmable chip, you always have to have this. I mean, this is a domain-specific processor, not like general-purpose CPUs. So you need domain-specific language to express what you want to do with this chip. So that language is actually called P4. So that P4 stands for Programmable Packet Processor. Right?
You mentioned the word fixed function. Can we compare what you're doing with what you have with GPUs with programmable shaders in a way?
Yeah. So the level of abstraction is also different, and the machine architecture is different. So GPU, for example, is especially GPU. It's a like vector processing machine. You have lots of computing cores, and then you can parallelize a lot of computing at the same time. So GPUs have their own unique architecture. This machine, PISA, is built for networking or packet processing. So it has packet parser and then multiple stages of processing, match action processing units. Every stage is exactly the same, and each stage you have quite a number of match action units that are all working in parallel to process the parsed packet contents. So architecturally, they're also very different. FPGA is completely different animal. I mean, it's just programmable gate array, so you can realize almost any logic, irrespective of whether it's compute intensive or messaging intensive. But at the same time, it's less efficient in terms of the cost and number of gates that you need to realize the same logic. So that's why FPGAs are often used for prototyping or the logics that naturally, inherently change a lot. So you have to keep changing, then you go to FPGA path. PISA is, on the other end, is a completely, it's ASIC, so it's as efficient as it can be, but it's designed to be programmable as an ASIC as well. Yeah.
So with P4, how can we think of this language?
Yeah.
Is it, it's not a general purpose language, but what can a programmer do, for instance?
P4 is designed to express network data plane logic very easily and highly intuitively. It's kind of declarative language. I wouldn't say it's entirely declarative, but the nature or the spirit of this is declarative language. So if you look at the P4 or the reference switch implementations written in P4, realizing all these widely used data plane protocols, the whole suite is only, say, 8,000 or definitely less than 10,000 lines because of these declarative characteristics. So you can, with P4, you can actually define your own new headers, looking just like C data structure. And then you can also define your own parsing logic, which is essentially just a finite state machine. You can introduce your own new lookup table. You don't need to tell how this lookup is actually done at the logic level. You just tell that, hey, these are the match keys for this lookup table, and then these are the actions that I want to associate with entries in this table. So you just describe that. You can also build your own actions that you want to perform, but these actions are built with some primitive actions, essentially primitive instruction sets unique to this PISA architecture. So as I said, this is for packet processing. Therefore, the instruction set is relatively simple. It has basic, Boolean and arithmetic operations with integers, packet header modification instructions like add header, remove header, update header. And then it also has some primitive state management instructions like register manipulations. So That's basically PISA. Yeah.
So maybe to help the audience understand a bit more what you can build with it, maybe you mentioned a really exciting example of network telemetry.
Yeah.
Let's talk about that.
That's a great question. So we came up with this flexible data plane technology and machine architecture PISA and the associated domain-specific language P4. We thought that we were introducing just programmability in networking. Then people came to us and then said that, hey, I mean, PISA is unique, it's interesting, but it's still a computing machine. It does certain things remarkably well. For example, it can handle billions of packets or maybe events arrive through the network. It can handle billions of events, I/O events in a second. It also gives predictable and guaranteed latency for each event processing, say typically sub-microsecond. This exhilarating performance is the unique value of this machine. And it also has some data structure support, like arrays or hashes and so on. And these are all programmable. So you can view it as a special type of computing machine. But on the other hand, it also doesn't do the real, complicated computing thing. For example, it doesn't have floating point operations. It doesn't have, say, the proper pointer kind of thing. It really doesn't have the stack pointer kind of logic either. Right? So you cannot introduce complicated data structure, but some certain kinds of data structure, especially that require constant time, lookup or operations, you can actually fit them and then express them in P4. And then once you do that, this is more than just networking machine. So that's why people started looking into all these possibilities. Still, going back to the networking. So, even in networking, there are innovations that can happen. For example, PISA and P4 allows people not to worry about introducing their own headers or modifying packets on their own. Once you have this kind of freedom, you can actually enhance your network visibility or telemetry significantly. So, for example, people came up with this idea called data plane telemetry as opposed to control plane telemetry. All the telemetry logic is actually running in the data plane at full line rate, so you can collect almost per packet information. So one example is technology called INT, in-band network telemetry. So essentially in this approach, packets are carrying the log information, network processing log information for themselves. So packets are delivering data, but it also carries the log information for themselves. So an INT switch, for example, receives a packet. In addition to forwarding the packets, as usual, it also adds its own metadata. Like I'm switch ID X, I received this packet at this port ID Y, I forwarded it out to port ID Z, and then it arrived at this time. It left this switch at this time. It observed exactly this much latency at this hop. It experienced queuing with this information. All this information is actually already available for every single packet in every switch. We just couldn't get this information out from the box because we couldn't modify the packets easily. Right? Now, with this freedom, you can do that, especially if you own your enterprise network or data center network. Every hop is yours. You own the end host as well. So even if you modify these packets in the middle, as long as you can strip this information at the last hop and then undo all these changes made to the packets, the application still continue to work and you collected per packet full visibility into what is happening inside your network. So imagine the possibilities that this opens up, right? This is an ultimate toolkit for your application performance monitoring. A lot of applications these days obviously run distributed and involves networking to some degree. And when something doesn't work or as user perceivable performance degradation happens, you need to figure whether this is my software problem, compute problem, storage problem, network problem. If it's network problem, is it happening at the NIC or virtual switch, physical switch? If it's physical switch, which physical switch? How do I debug all these things today with network? It's almost impossible. And it's such a stark contrast between the way people manage and maintain compute or storage applications, right? Compute and storage, these are all software these days, and then people can instrument almost at any level, right? They can log almost every single instruction level. They know exactly what happened. So when something went wrong, they collect all this information. Once some analysis tool realizes that, this logic was a problem. In networking, Nothing like that existed, right? People are still using ping and traceroute, SNMP, which were, invented 30 years ago. They're using the same tool. And so that picture is entirely changing with this data plane telemetry capability. So that's the innovation that happens in the networking field with this data plane programmability. But this innovation goes to the other part of the industry as well. So people are starting to build extremely fast, but a little leaner in terms of feature set, leaner middle boxes, like layer 4 connection load balancer or DDoS detectors or your TCP SYN authenticators or something like that, because data plane programmability gives you such possibilities. And obviously, the kind of things that these kind of boxes can do compared to what software can do, it's a smaller feature set. But still, the value of this kind of device is that it runs at, say, multiple terabps. It can handle billions of packets or queries a second. And so it's extremely robust against availability attacks like DDoS. So that's the unique opportunity that this kind of machine or PISA architecture opens up. Last but not least, most important innovations, in my opinion, that will happen is the applications that consider PISA as computing or part of computing or storage systems. For example, people have started talking about offloading part of the Paxos protocol, consensus protocol, down to the switches or the networking system. And if you, say, realize Paxos learner or processors, then the number of Paxos or consensus messages this system can handle is like 2 or 3 orders magnitude higher than the software implementation. And if you think about it, consensus protocol is really not computing, because the amount of computing that you need to do to handle each consensus message is not that much. You essentially, check the sequence number and then make sure that this one is larger than the last known sequence number or not. So it's essentially message handling kind of workload. And so those kind of things are particularly well suited for this PISA architecture. People have also started talking about even some storage applications or maybe something in between compute and storage. For example, we have written this paper called Netcache and published it at SOSP last week. So essentially, you're realizing small but extremely fast memcached cache that load balances multiple memcached servers located in the same rack, for example. So suppose you have 40 memcached servers. Unfortunately, today, because the popularity of key value items are significantly skewed, a small number of servers out of 40 will hit its utilization maximum very quickly. And at that point, the tail latency of read-write operation is already long enough. So you declare that, okay, this entire cluster has reached its own maximum. So even if you have, say, 40 servers, the actual net aggregate throughput gain you get is, say, 5x, at most 10x. But the theory indicates that if you can introduce a very small but extremely fast cache in front of these 40 servers, then if you cache only, say, n log n number of hot items, where n is just the number of servers, so 40, so n log n is still pretty small, then the theory tells that, hey, the utilization of these 40 servers can be pretty similar within a very narrow bound. So essentially you achieve 40x throughput increase thanks to this small but extremely fast cache. So something like this can be very easily realizable with this kind of PISA machine, because PISA machines has its own, on-chip SRAM. So this kind of, in my opinion, jointly optimizing your compute or storage applications along with the network on which these applications run, that opens up a lot of possibilities.
It's really exciting, and I'm particularly excited about this telemetry stuff because it sounds a bit like distributed tracing, where you annotate requests along the path, but with you, these annotations take no extra time. As you say, they run at, we call it line rate, I think?
Yeah, full line rate, say typically 6.4 terabps with the fastest chip available today,
So I find it really exciting. Maybe it's just me. But.
Yeah, no, it's a lot of people express the same sentiment here.
Yeah, we had lots of great comments. I was wondering, there's no FPGA or anything in your machines. How does the programmability actually work?
That's something that is not that easy to explain without, say, a PowerPoint slide or whiteboarding, but let me try. Essentially, the key components that allow this programmability at full line rate are programmable packet parser and then programmable match action units. Stages of this match action units. So programmable parser essentially is parser is a machine or a component that receives a sequence of bytes and then generate parsed result. So you essentially have some number of containers with certain sizes. Given an incoming packet, you read through the first n number of bytes and then slice each header fields based on the specification and then move these header fields into these containers. So that's what parser does. And programmable parser essentially allows you to express your own state machine using something like ternary cam and so on. So that's one component. The other component is programmable match action unit. One match action unit, for example, is just nothing but a collection of, say, SRAM or TCAM combined with simple ALUs. Right? So SRAM and TCAM are there basically to realize match logic, and then ALUs are there to execute the actions, essentially simple instruction sets. MAU is the term that we're using to represent match action unit. So each MAU unit essentially can handle one lookup, and that lookup can lead to, in networking, always at most one match or no match, and depending on what happened, you can actually exercise the associated instruction along with some instruction operands. And then you have several number of these identical match action units in one stage, so that you can parallelize a lot of things that can happen at the same time. And then you also have multiple stages laid out in sequence so that you can actually realize some dependencies as well. But again, these stages are exactly identical. So all the MAUs are identical. That's why this is now a very good compiler target. And this sequence of stages are useful to realize some, read-write dependencies that is expressed in your P4 program.
There is hardware available for this already. There's multiple companies that make this, right?
Yep. And Barefoot is one of such companies. Yep.
Maybe to wrap this up, why is this only coming now? Why have people not figured this out 10 years ago? Or was it already there, but we don't know about it? Or what do you think?
That's a great question. Again, it's not that easy to explain without some visualization aid. But again, let me try. So when you build a networking ASIC, high-speed networking ASIC, there are a few functional units that you have to always add. So one of them is called MAC and SerDes, serializer/deserializer, essentially converting input byte stream into parsed representation. And the reason this is hard to realize in electrical engineering world is because it runs at extremely high speed. For example, even say CPU core or our PISA core runs at say 1 gigahertz. This has to run at say 25 gigahertz because input bits are arriving much faster. So this logic is what is called MAC and SerDes, and this roughly takes say 1/3 of any networking ASIC today. The interesting observation here is that this MAC and SerDes has nothing to do with logical programmability. Whether you build fixed function chip or not, you have to have certain amount of MAC and SerDes capacity if you want to declare that, yes, this is 6.4 terabps chip or 12.8 terabps chip. So that's the biggest portion, lion's share. The second portion is the memory that you need to host tables or packet buffers where the actual switching happens. Again, these tables and memory have nothing to do with whether you have programmability in logic or not. If you want to declare that my chip can host this much or this big routing table, or it has this much of packet buffer, you have to have that, right? So that's the second portion, roughly say 20%. The third portion is what we call wires or routing. Networking chip, the unique part about networking chip, it has lots of wires working in parallel because this large number of bits carrying this parsed representation. I use the term containers here. Containers carrying these packet header fields. They have to go around almost every corner of this chip. That takes a significant portion. So that's the third portion, again, maybe say 15 to 20%. So all these top three portions are irrelevant to programmability. Now, only the fourth portion is the logic through which you realize particular protocols such as IP, VLAN, Q-in-Q, MPLS. If you're familiar with network virtualization, something like VXLAN, that's implemented in logic portion. That's like already the fourth portion in terms of the size it takes in the switching ASIC. And then it's getting smaller and smaller because the other portion, the top three, get increasing over time, over generation, because you have to build a larger chip with more capacity, more memory, and more containers. So relatively, the portion that this logic takes gets smaller and smaller over generations. And finally, we're at a point where this difference introduced because of programmability in logic portion is insignificant enough compared to the whole ASIC size. So that's why the industry is realizing, programmable ASIC, now we can do that. The cost is there, but it's insignificant, economically irrelevant. So that's what is happening now.
I think the audience is now excited to check out P4. I guess there's websites and all kinds of things.
Yeah. So the P4 is sort of industry-wide domain-specific language for all these programmable packet processors. Actually, it's more than PISA machine, meaning that there are P4 programmable FPGAs. There are P4 programmable NPUs. By the way, NPUs are a special kind of CPUs that has some special feature adds for networking. A lot of people use NPUs to build sort of feature-rich networking solutions. So FPGA, PGA, and NPUs can be programmed in P4. They're working, though, in a slightly different performance range than ASIC. ASICs work at multiple terabps. NPUs and FPGA is still sort of an order of magnitude slower range than ASICs, but they offer you more functionality and flexibility. Programming FPGA, I'm not sure whether you have done that, but it's not trivial. You have to synthesize this, and then you have to worry about timing and those things. So if you can program FPGA using P4, you can actually accelerate your innovations very easily. That's why FPGA guys are adopting this. NPUs the same. NPUs offer a lot of flexibility, but you have to do something called microcoding. And you also have to worry about performance degradation upon workload. So P4 allows one to build networking applications more easily with these kind of targets. But more interesting thing is that even software switch guys are adopting P4. For example, OVS, one of the most widely used software switches available in Linux kernel, they are also adopting P4. And it's kind of, when you first hear about it, it's kind of strange because software switches are already programmable. But why do you introduce yet another layer of programmability such as P4? And the reason is that, yes, software switches are actually programmable, but how many people out there can actually read Linux kernel, tens of thousands of lines and then maintain that? And then even if you added your own new logic or protocols, if you cannot upstream it to Linux kernel, how can you maintain that easily, right? So there is all problem associated with deployment and so on. So, but if for example, OVS comes with the P4 programmable version, then you write your own P4 program, say a few hundred lines. OVS goes to the next version. That's fine because you just need to recompile your P4 program, and that new version of OVS will still support it. So that decouples, a lot of hairy issues. That's why even software switches are adopting P4 now.
So we'll point our audience to the relevant websites.
So the website is p4.org. That's the language consortium that nurtures this entire P4 and programmable data plane ecosystem. And it's entirely open source community. Everything is Apache 2.0 based, free of charge, free of commitment. You just enjoy whatever is there. Or if you want to contribute, just join as a member, and then you can start making contributions at the code level or spec level, or a lot of things are possible there.
So audience, you know what you have to do. Check all these things out, and thank you, Chang.
Thank you.